Welcome back to the ChemDoctor, and this would be the fourth video in the series on gases. And what we're going to do in this video is work an ideal gas problem utilizing PV is equal to nRT. All right, and the origin of this equation, PV is equal to nRT, comes from the combination of the empirical laws, where Boyle's law, Charles' law, Avogadro's law, and Guy-Luzak or Amonton's law is combined into one equation. So you'll notice that all the variables here are related. The only thing new in this equation, although I've already introduced the concept in previous videos, is this thing called R, which is the gas constant. So I'll draw your attention to its value down here at the bottom of the screen, and you can see that it's equal to this number 0.0821. The crucial thing, actually, and more important than the number itself, is to pay attention to the units on the constant. It's equal to liters times atmospheres divided by mole times K. So the main thing is that anytime we use this equation, you need to be certain that all of your units have been converted into the correct units relative to the gas constant. So pressure units need to be in atmospheres, volume units need to be in liters, the particles need to be in units of moles, and the temperature needs to be in units of absolute temperature Kelvin. Alright, so let's take a look at what we're being asked here. We have an aluminum scuba tank that has a volume of 77 cubic feet. It's at 80 degrees Fahrenheit, sitting on the shore of the lake or the ocean, whatever, and the tank contains a gas that is at a pressure of 3,000 psi's. And the challenge is to calculate the total moles of gas that are contained within the steel tank or the canister. So the thing that I want to do first, and I want to emphasize this to the viewer, is that you need to be drawing pictures of your gases. Make sure that you use a picture, and in the picture you want to be certain that you have indicated all of the information that you've been given in terms of any specific problem. So let's go through on this. I've drawn a picture of a tank, and I'm going to indicate its volume. So its volume is 77.4. Make sure to put in my units. These are going to be units of cubic feet. The pressure is 3,000 psi. Make sure to write the units in there. And then let's see, my temperature, T, is 80 degrees Fahrenheit. Okay, typical more or less winter day here in Phoenix, about midday or so. And then the moles will be small n, and that's what we're solving for, so question mark. Now, we're going to be using PV is equal to nRT to do this. And why don't we start by actually solving for the moles? And we're going to do that without putting any numbers into the equation. Number two, we can't put the numbers in there yet anyway, because none of the numbers are in the right units. But you should always use good math skills here, or habits, and the main one being that you want to solve the equation for the variable you're interested in before you ever insert any numbers. So the first thing I'm going to do is flip this equation around, so it's nRT is equal to pressure times the volume. Then what we're going to do is divide both sides by RT, because we want to get the moles by itself. We see that the RTs on this side cancel out. Whoops. The RTs on this side cancel out. So we're going to have N is equal to pressure times the volume over RT. So there's the formula that we're going to be using. Now let's go ahead and deal with the units. And we see that in every single case we need to make a change. So let's start with the PSI, since I kind of think that they're, well, not necessarily easier than the volume issue, but okay. So what's going to be the conversion for PSIs? All right, so you need to realize that 1 atm is equal to 14.7 PSIs. And you know what? Just in case you're rusty with pressure unit conversions, I'm going to go ahead and put all the rest of them in here too while we're at it. So 1 ATM is equal to 14.7 psi's, 760 millimeters of mercury, 760 torr, and 101,325 pascals. Or sometimes this unit will be given to you where it's converted to kilopascals, and in that case it'll be 101.3 kPa's. So you can maybe write this down somewhere in your notes, or you can come back to this video to review the situation, but these are the typical pressure units encountered in gas problems at the college level and at the high school level, and so you really should have these committed to memory, so you're not having to look them up when you're trying to do the problems. So getting back to this issue, the issue at hand here, we need to convert our psi's into atmospheres. So we're going to multiply times 1 ATM divided by 14.7 psi. All right, and you can see that what's going to happen is the psi's cancel out, and we've successfully converted this into ATMs, which in this case will be about 204 atmospheres of pressure. All right, now let's do the volume next, because that one's actually easier than the degree Fahrenheit issue, because with the Fahrenheit we're going to have two calculations that are going to need to be done. So let's deal with our volume. So on the volume, the important thing there is to realize that a cubic foot is equal to 28.3168 liters. So using the same kind of unit multiplier method, it's going to be 77.4 cubic feet over 1. And then that's going to be times our liters, which will be in the numerator. So 28.3168 liters. And that's over 1 cubic foot. Okay, cubic feet cancel out, and we have solved for liters. And you can see that we should be getting a big number. A scuba tank is it's a big volume, so it's going to be 2,192 liters of gas in a scuba tank, in a typical recreational aluminum scuba tank. All right, now let's deal with the temperature. The temperature is actually a pain, and in my classes I tend not to use Fahrenheits, but since we're dealing at all, because they're such a pain in the neck. But here's the deal. With the scuba tank example, we really have to, because if you're in the United States and you're about to go diving, you're going to be looking at a temperature factor that's in Fahrenheit. So, all right, let's see what we're going to do. So we have two calculations. First thing we're going to do is take this 2 degrees centigrade, and the equation that we need is down here at the bottom of the screen. So degrees centigrade is equal to Fahrenheit minus 32 divided by 1.8. So to get to degrees C, we're going to take our 80 and we're going to subtract 32 from it, and we're going to divide by 1.8, and so we're going to get 26.7 degrees centigrade. Now, to get to Kelvin, because remember our constant is in units of absolute temperature, which is in Kelvin. Kelvin is much easier to find the K. We just simply, the conversion will be equal to degrees centigrade plus 273. So we take our 26.7 and we add 273 to it. Whoops. We add 273 to it, and the Kelvin degrees that we're going to get here is 300K. Okay, so now we're ready. Now we're ready to use the ideal gas equation. I'm going to circle each of the units that we're interested in. Here's our pressure, 204 atmospheres. Here's our liters, and here's our temperature. So now we can go over here and we can use our equation. All right, so the moles of gas the moles of air, actually, to be accurate about it. Remember that your air is composed of about 79% nitrogen and about 21% O2, oxygen. So we're finding the total moles of gas, which is a mixture of these two particular gases. So the moles will be, all right, so we're going to have our pressure, 204 ATM times our volume, which is 2,192 liters. We're going to be dividing by the gas constant, so 0.0821, and I'll make sure to put my units in, liters times the atmosphere, over mole times K, and then our temperature, which is 300 Kelvin. So the moles of gas in a standard aluminum scuba tank will be 18,155 moles of air. All right, now, if we assume that, well, all right, so this is going to be the total moles of air that's available to a diver who's about to dive into the ocean and go, maybe they're going to drop onto a reef to look at the fish. If we assume that the fraction of nitrogen and oxygen is 79% of the total volume of gas, and 21% for the oxygen of the total volume of gas that's captured within this canister. And since pressure is proportional to the total number of particles, then we can assume that these particles are evenly distributed throughout the whole tank. Then we literally, to figure out what proportion of these particles are oxygen, all we have to do is multiply the 18,155 times 0.21, and so the actual moles of O2 available to keep the diver alive will be 3,800 and about 13 of them, and the rest is nitrogen, which is inert and of not really of any use to the diver as far as like keeping the diver alive. Alright, and with that I'm going to go ahead and close the video.